As we look at different functions, here's an example of a function. It has what we call a maximum. You can see that that is a spot on the graph that is bigger than everything else immediately around it. But is that the biggest spot on the graph? It is not. So we don't call it just a maximum. We call it a local maximum. Because, you know, there's a spot that's bigger, but right in this general area, it's the biggest one. And then we got this spot right over here. We don't just call it a minimum. We call it a local minimum. And in calculus, we talk a lot more about what it means to be a local minimum and local maximum. But those spots on the graph are extremely important because as you can see, we want to be able to talk about applying maximums and minimums to the real world. So for example, if you're running a company, would you like to maximize profit? Would that be a good thing? Would you like to minimize costs? Would that be a good thing? I had a calculus teacher in college. He was awesome. His name was Mr. Mike, Dr. Mike. Mike, if you're listening, thank you. You made math a lot fun. Well, math is always fun. So, yeah, you're just a great guy. So anyway, he worked at the Mayo Clinic, and he worked in an office where doctors would come to him and say, "I've got a problem. Can you help me work through this issue?" And he told me, he said, "Yeah, one time, doctor came to me and said that I have a patient who's got an artery. What travels through an artery? Blood. What sometimes happens to an artery? Gets clogged. Why do arteries get clogged? Why does it happen? Too much steak? Okay, too many porterhouse and ribeye steaks. Okay, there's a number of things in your life that can cause clogged arteries. You know, smoking is one of them. It's a huge issue for heart disease. Anyway, so here's what we have. All of a sudden, you get this clog going on. What do you do? Somebody's got a clogged artery. What's going to happen to them? Heart attack, right? Heart attack. It's like me, what happens? You got a blockage. Uh-oh, blood can't go through. Blood's going back up in the heart. Boom. Right? So what do? Somebody's getting a clogged artery. What do? You don't know. It's so cool because it's so obvious. You can't even think about it. This is what doctors really just do, the obvious things. They say, well, we'll go around it. So that's what we call a bypass. Have you heard of a bypass before? They bypass it. They're like, okay, roadblock, go around. Okay, so they literally cut a section of the artery open here and there, and they put on a new branch of an artery. So that way the blood, as it can't go there, it goes back up and around this way. Hey, I mean, that's what it is. What if that gets blocked? Oh, I've never heard of a double block. That would be cool. You know, if you heard of a, you know what I mean? Well, yeah, maybe not cool. Maybe not cool. But so anyway, doctor comes to him and says, hey, so I've got this artery. It's got a block in it, and we're gonna have to put a branch on it. So we're gonna branch the artery. And he said, I'm wondering, because it's got a block down here. He said, I'm wondering what angle do I put the branch at? He said, what do you mean? He's like, well, here's the issue. He said, I know that there is friction to blood flow. And the friction can wear on the joint. It can wear on the artery itself. He said, I want to reduce the friction of the blood flow. He said, what angle do I put on that to minimize the friction of the blood flow? Does that sound like an important thing? And he was able to solve it. In fact, I do the same problem with my calculus class this year. I walk them through it to show how people use mathematics and these applications to save lives. I mean, it's real stuff, okay? And so maximizing, minimizing, super important. So we're going to investigate really the basics of that concept. You'll get into deeper ideas next year in calculus as you look at it. It's pretty cool, but once again, you learn that math saves lives, right? How about we save lives today? Here we go. All right. We start with a parabola because a parabola has a maximum or a minimum. For example, if we have f of x is equal to, parentheses, x minus 3, plus 3, quantity squared, minus 2. You just had a test where you learned how to graph that. In fact, you learned how to graph it, boom, just like that. Because what's the horizontal shift? Left 3 and then down 2. So you could sketch this really quickly, couldn't you? You know, like that location right there is -3, -2. Right? So it has a minimum value of -2, and that happens when x is -3. Done. Super easy. So tomorrow we're going to investigate what we call vertex form of a parabola. But today we're going to investigate what we call standard form, and that's the one you actually know more about. It is really key in your focus in intermediate algebra when you took that class, and last year when you took advanced algebra as well. And so we're going to review that today for just one day, and it starts with this idea of how do we find that vertex if it's ax squared plus bx plus c. So if you had like y is equal to x squared plus 4x minus 1, do you know how you would find the vertex? Do you remember the formula? It's in your brain. I'm going to help you locate it. Do you know the quadratic formula? What is the quadratic formula? Very good. You know that, right? Well, that's the vertex. Think about it, folks. The quadratic formula helps you find these spots where it crosses the x-axis, right? So that is your negative b over 2a. So you go from negative b over 2a, you do plus square root of b squared minus 4ac over 2a, and you go minus square root of b squared minus 4ac all over 2a. So you just start with the vertex, and then you go one direction, and you go the other direction. That's all the quadratic formula is doing. From your vertex, it's just moving. So as long as you always just remember the quadratic formula, which you always do, you're going to be able to identify the vertex. So the vertex happens at negative b divided by 2a. Once you have the x value, how do you think you come up with the y value? Plug it in. So I'll write that as f of negative b divided by 2a, meaning we plug it into the function. Not too bad, huh? All right, flip it over. Let's do two examples. We're going to sketch a graph of this parabola, and we're going to state the coordinates of his vertex, intercepts, and some other things. First, we're going to talk about the direction. We're going to talk about the vertex. We're going to talk about the axis of symmetry. We're going to talk about the y-intercept, and we'll talk about the x-intercept. We're going to do all these. And this is a nice one. It goes pretty quick and simple, so I think you guys are going to be good to go. So let's start with the basic one. It's starting to heat up in here. Start talking about parabolas, it just gets exciting. Hey, how about Rose last night, huh? 50. Derek Rose drops 50. What a kid. I heard he cried afterward. Did you see that? Good for him. I mean, talk about a guy that's really been down and out and has some struggles. Hasn't exactly been the best role model, but he's climbing back. Thank you. Well, you know, it's always track season, right? All right. Direction, up or down, right or left? What do you think? Which direction is this thing going? Up. Why? Because it's a positive 2x squared. Any confusion there? Great. I mean, these are the first problems on your test, okay? These are the very first problems you're going to get. The vertex, I have to do negative b divided by 2a. So it looks like a is 2, b is 0 because we don't have anything in front of an x. Or I should say we don't have an x, so 0 is a number in front, whereas c is negative 8. So you have to be able to identify a, b, and c. Any questions how I came up with those? So negative b divided by 2a would be negative 0 divided by 4, which is 0. If I plug in 0, what do I get? Negative 8. That's the vertex. I'm going to make a little graph. I already know how this is going to turn out, so I'm going to make a graph to this scale. I'm going to go by 2 units on the x-axis. I'm going to go by 4 units on the y-axis. And that's my little graph. I'm going to plot the vertex. I'm going to draw the axis of symmetry. The axis of symmetry is a line that passes through the vertex. It's a vertical line, and it divides the parabola directly in half. I want to write the equation for the axis of symmetry. That's a line. It's a vertical line. Do vertical lines have the equation x equals or y equals? Which one? X equals is the equation for a vertical line. So anytime you see the axis of symmetry, it's x equals, and it's always just the x value of the vertex. Easy peasy. Any question there? The y-intercept happens when x is equal to 0. Plug in 0 for x. What do you get for y? -8. In fact, the y-intercept is just always whatever your c value is when the vertex is in standard form, right? So if you had y equals ax squared plus bx plus c, if you plugged in 0 for those spots, they would just go away. You'd be left with c, right? So c is always the y-intercept. Now we got to do the x-intercepts. Well, the x-intercept happens when y is equal to 0. So 0 equals 2x squared minus 8. How do we solve something like that? Factor it or quadratic formula, right? I'll take 0 equals 2 times x squared minus 4. 0 equals 2 times x plus 2 times x minus 2. So I have x-intercepts of plus or minus 2. Yeah? All right. Let's plot them. Now, sometimes when we graph this stuff, people are like, well, how accurate of a graph is it really? I'm just going to quick produce this graph, 2x squared minus 8, delete, delete, delete. And I'm going to go into my window, and I'm going to make the x values -4 to +4, tick mark every 2. Y values -8 to +8, tick mark every 4. And I'm going to generate this graph and see if it is a close representation. What do you think? Spot on. So we're able to produce extremely accurate graphs in this situation. Don't flip over, but you can look at mine. If you were to flip over a sheet, you'd see standard form. All these pieces are listed out for you. Direction, if A is positive, it's up. If it's negative, it's down. Here's your vertex formula. Here's your axis of symmetry. X is always the x value of the vertex. Y-intercept is C. And here's how you find your x-intercepts, quadratic formula or factor. Piece of cake, upside down. We do one more problem, you get your worksheet. Worksheet today and tomorrow. No book assignment today or tomorrow. Here we go. Direction, vertex, axis of symmetry, y-intercept, and x-intercept. All right. I already heard Dane say that the direction is down. Why is the direction down? Because it's a -1/4 x squared. How do I determine the vertex? What is -b? 6 divided by 2 times -1/4. -1/2. 6 divided by -1/2. -12. That means I already know the axis of symmetry, don't I? I want to be clear, folks. If you write -12, I'll mark it wrong on the test. It's an equation for a line. You must write x equals -12. I will not budge on that. It's not simply a value. It's an equation for a line. How do I determine the y value? Plug it in. -12 squared is 144. Divided by 4 36. Make it negative. Negative 6 times negative 12 is positive 72 plus 3. Negative 36 plus 72 is positive 36 plus 3, 39. That's our vertex. What's the y-intercept? 3. That was easy. Let's find the x-intercepts. 0 equals negative 1/4 x squared minus 6x plus 3. Where do I even start? Yes, on your calculator you have the quadratic formula, don't you? I want to be clear. I will allow you to use that to produce the decimals, but I will also ask you to express it in simplest radical form on the test. So let's come up with the decimals right away. Somebody go to quad form, execute, type in negative 0.25, negative 6, and positive 3, and tell me the decimals that you get. You get 0.49 and negative 12.49. Whoop. Sorry. Just trying to remember from the other class. Stop yelling at me. It's an interesting looking 4. That's my 4 when I mess up and I write a 2 first. So, all right, so we got 0.49, negative 24.49. Good. So let's do the simplest radical form and make sure it matches that. So I have to use a quadratic formula, don't I? Anybody know what I could do to make my work easier? I don't like the fraction. I'm going to multiply by negative 4, which you can do because what is 0 times negative 4? Stays 0, so that's fine. I get a positive x squared. I get a positive 24 minus 12. Oh, 24x, sorry. Now I could use the quadratic formula. Negative b, positive 24, plus or minus the square root of, what's 24 squared? 576 minus 4 times a is 1 and b is negative 12 divided by 2a. Take out my handy dandy calculator. 576 minus 4 times 1 times negative 12. And you can see that we get 624. Go away. 24 plus or minus the square root of 624, negative 24, thank you, divided by 2a. I have to reduce the square root of 624. Off the top of my head, I don't know a perfect square divides evenly 624. Somebody want to make a guess? Let's guess 16. Sounds reasonable. 39. Great. So if 16 goes in, it would be 4 roots of 39, right? Yeah, 16 works. So we've got negative 24 plus or minus 4 roots of 39 all over 2. Can I simplify that? Divide by 2, and I get negative 12 plus or minus 2 roots of 39. Now, if you don't have the quadratic formula plugged into your calculator, do it, because some guy made a 4-minute, 2-second video on his calculator or on his YouTube channel for you for that purpose. But if you didn't, you could type in negative 12 plus 2 roots of 39 And you can see you get the 0.49 that we were talking about. And if you take the same entry that we just had, and instead of a plus, change it to a minus, you can see that you get negative 24.49. So the last thing to do is just graph it. I'm going to make a 40 by 40 graph. My vertex is negative 12, positive 39. The axis of symmetry runs right through that. The y-intercept is positive 3. And the x-intercepts are located at about 1/2. That's going to be really close to the y-axis there. And then 24, negative 24.5. So again, I'm just trying to make estimations, but and I've got my graph. Negative 0.25x squared minus 6x plus 3. Window, negative 40 by 40. Tick mark every 20. Negative 40 by 40. Tick mark every 20. Pretty much spot on because we're amazing. Good work. Later, YouTube Nation. Thanks for tuning in. Another great day to do quadratics.